We're going to continue our study of energy by talking about springs. I think the reason they add springs in here is because they want you to have another type of potential energy to deal with, not just PE equals mgh, but now the potential energy stored in the spring when it's either stretched out or compressed. First, we're going to talk about forces in springs. And Hooke's law, we're going to write an equation for it. It's going to be Fs, the force in the spring, equals Kx. K is called the spring constant. I'm going to put quotes around constant because it's not a constant like the universal gravitational constant, big G. The universal gravitational constant is 6.67 times 10 to the minus 11 everywhere in the universe. This spring constant is only constant for that spring. If I have a particular spring, no matter how far I stretch it or compress it, the spring constant stays the same for that spring. But when I switch to a different spring, maybe it's a stronger one, it's harder to pull out, it's going to have a different value of K. And this is a measure of how stiff the spring is. Okay, a stronger spring is going to have a larger spring constant. X is the distance from equilibrium that the spring is stretched or compressed. It's not the length of the spring, so don't make that mistake. And if I was to graph X versus F for one of these springs, okay, X and Fs, that's a direct relationship, so it's going to be a straight line going up like this, and the slope would be the spring constant. Now I have Hooke's law in quotes there also because it's not a law like the universal law of gravity where any two objects feel it. Not all springs obey Hooke's law. If it obeys Hooke's law, it's going to be a straight line like that. If it does not obey Hooke's law, it's not going to be a straight line. Okay, so maybe something like that. But for the springs we're going to use, they're going to obey Hooke's law, and it's going to be a straight line. So here's an example. The spring is 0.4 meters long. It stretches to 0.6 meters when a 10 kilogram mass hangs from it. What is the spring constant? So we're going to kind of draw this. Maybe it's suspended from a ring stand, and it starts out here. This is the equilibrium length, and this is 0.4 meters. Okay, between there. Now when I put a weight on it, it stretches down. This is a 10 kilogram mass, and it stretches to a length of 0.6 meters. So we have to think about what force is acting on it, because our equation is going to be Fs equals Kx. So the force down here is the force of gravity down is going to be 100 newtons. And the spring force is pulling back up on it. And it also has to be 100 newtons because this thing is sitting still there. So 100 equals K. Now, X is the distance from equilibrium. So the original length was 0.4, and then it stretched to 0.6. So X is 0.2. And then K would end up being 500. It doesn't have its own unit, but this was in newtons. This was in meters, and I divided newtons by meters. So newtons per meter is the unit for our spring constant. So those are pretty straightforward problems. Now, where this gets a little bit more important is when we have energy in springs. Okay, there is potential energy stored in the spring. The equation for it is going to be PES, potential energy stored in the spring, is 1/2 KX squared. And then you're going to have problems something like this one here. Okay, a spring with a spring constant of 80, so they're giving you that K equals 80 newtons per meter for this spring. It's compressed to 2 meters. It is then used to fire a 1 kilogram mass across the frictionless surface and up the slope, and it comes to rest at point C. And it wants to know the speed at point B and the height at point C. So again, we have to identify our points. We have B and C. But I put back here point A where the spring is compressed because we actually know the most information about that. So PE point A. Now the gravitational potential energy is going to be 0 because the height is 0. The kinetic energy is going to be 0 because that's where it's being released from. It's not moving at that moment. But now we have this spring energy we have to add in. So it's 1/2 kx. That's 1/2 times k was 80. X is the distance it's compressed, so that's 2. I have to square that. And that gives me a PES of 160 joules. And then I find my total energy. And that's going to be 160 joules. Now, we want to look at it B because it says what's the speed at point B. So at point B, its gravitational potential energy is still 0 because the height is 0. Now it's going to have some kinetic energy at this point. So 1/2 mv squared is 1/2 times 1 times v squared is 0.5 v squared PES. Now, it's no longer attached to the spring because once the spring gets to its equilibrium position, the mass flies away from it. So there's going to be no energy stored in the spring because x equals 0. So now our total energy is equal to 0.5 v squared. Now what you're going to do is set your total energies equal to each other. So E total at A equals E total at B. So 160 is 0.5 v squared. That gives me 320 is v squared. And that gives us a velocity of 17.9 meters per second. Now, we want to know how high it goes at C when it comes to rest at point C. That's the highest point. So we can do the same thing for point C. PE, now it has PE because it has height, so it's mgh. It's 1 times 10. Now, we don't know what the height is, so we're going to leave that as h. So is 10h. KE is 0 because it comes to rest there. And the PES is 0 because it's no longer attached to the spring isn't compressed. And now our E total here is 10H. Now I have to set that total equal to another total, and I already know at A the total is 160, so I'm going to E total at A equals E total at C. So 160 equals 10H, so H is going to be 16 meters.